分辨率，那个 R， 应该会是3300。如果你有写到那一题的话，我不确定，我有检查，但我不确定我有没有每一本都检查到。或者是加一下总分，看我有没有加错。
Talk about cone spiral for the diffraction. Just try to remind you for the diffraction theory, we have the far field diffraction, and you saw this before. If I just pull out one thing like this is a far field diffraction because the distance I observed this pattern is far away from the aperture. And also the distance is much longer than the reference. So this is a far field diffraction. This is another far field diffraction. It's a single slit diffraction. Okay, and we call this Fraunhofer diffraction. Basically, the diffraction pattern is a Fourier transform of the aperture. So this is a basic concept for the Fraunhofer diffraction. So a sinc function, if you have a slit, then it's a step function, it's a square aperture. So the square wave, the Fourier transform of the square wave is going to be a sinc function. So what you are seeing here is the sinc function. Okay, so this is sinc function intensity. But what happens is that if you go to near field, the story will be different. When I say near field, this means that we are looking into this. And if you look closely, the diffraction pattern here is very different from the Fourier transform of this square aperture. So now, imagine that you come over and then you look into the diffraction pattern here. And you see 5 structures. Okay, and that is the topic we're talking about right now for air diffraction. So can you imagine that? Well, look at this. This is far diffraction. This beautiful sinc function. But then I transfer here, and I suddenly find that hey, it's not a sinc function. Then this is what we want to find out. Okay, and so after we went through the theory, we found that you need to look into this integration. The phase term is quadratic in terms of the aperture of the coordinate. So you need to evaluate this term. And when you evaluate this term, you have real part, imaginary parts. And then you end up, if you have a width of the slit, expand from this value to this value, then you have to do this equation. Okay, so that, okay, right? It's just well, regardless of how the development of the theory, how the derivation of theory, you end up having to evaluate this value. All right, right, then let's define this to be two values, real part, imaginary part, starting from 0 to something, okay? And if you do an integration from 0 to infinite, then you have a constant value like this. All right, and if you plot this on the complex plane, it corresponds to this point. Okay, and for other values, it's going to be along this spiral curve. For example, if you set this value to be 1.5, then you'll be looking at this point. The C and S value will be right at this point. This is a complex plane. So can you imagine that? Welcome, Yonanis.
Hello, hello.
It's
Good morning.
must be quite tough for you. I know that how difficult it is when you travel and then you have to attend the class.
And it's okay, you just came up from Sweden, so
Yes.
you're feeling the same, right?
But we all work very hard, and in another 2 weeks we'll be free from this class. Wow,
And
so
it's a good class.
let's push a little bit. Well, you missed quite a bit of the experiment, and I was fronted time to show you the experiment again. Anyway, so we just went through the simple experiment. In the far field, you get the Fourier transform of this aperture and this sinc function. When you move the patterns close to the screen, you found that this is not a sinc function anymore. And in the near field, you have to look into this integration, okay? And then if you have two aperture boundaries starting from W1 to W2, then you will do this integration. All right, so we understand that the integration will give you a real part and imaginary part. So let's take a look at how this value will vary depending on the argument in this integration range. Okay. For example, if we set this the upper bound of integration to infinite, then turn out that you get a constant value of 1/2 plus 1/2 I. That corresponds to this point on the complex plane. Okay, and of course, if you change this value to other value, for example, 1.5, then you will have some other value. And then people already calculate that and tell you that, hey, this value is here. Okay, if you set this argument to be 1.5, then you on this complex plane, you'll be looking to this point. So if you finish all the calculations for all possible values, then you're going to have the values fall on this spiral. And we call this corner spiral. But if you have a negative value here, then it's going to fall on this plane. So this corresponds to minus 2.0, minus 5.0 perhaps, and minus 2.5. So if you have a value here, that is the negative number, then you will be walking on this spiral. All right, so we call this corner spiral. Any question about this? All right, we have been slowing down the lecture a lot because I figured that perhaps it's more important for you to understand it instead of giving you a lot of materials. Okay, so Yishan, can you catch the concept now?
Yeah.
Well, basically, when you move the diffraction pattern to very close to the screen, then the Fourier transform relationship fail. You have to evaluate the quadratic term in the face of this integration. And that's why we look into this. All right, so if I have an aperture with two boundaries between this one and this one, you'll be evaluating the difference between two vectors on this screen, right? If you set a boundary between these two, then then you'll be subtracting two vectors given W1 and W1 and W2. If you change the integration boundary from W1 to W2, then you'll be identifying this value at W1 for one vector, and then identify this two values at another vector, and if you do a subtraction, you'll be evaluating the difference between the two vectors, right? Because, well, let me write it out. If you know this integration, exponential I, 1 half I W squared dW, and then you get this C plus I S. So if you evaluate from OP1 to OP2, you'll be doing C W2 plus I S W2 minus C W1 plus I S W1. You'll be doing this calculation for these two boundaries mathematically. So, Li Xiaolong, this is reasonable to you, right?
Yes.
Because
So for the first case, we would use W1 to be 0, so it would just be.
but if this W1 to be 0, then this is going to go to 0. Okay, because basically you set this integration, you set this to be equal to 0. 0 from 0 to 0, you get nothing. Right. All right. So if you have two boundaries, two slits, W1, W2, two boundaries, you just need to integrate over the opening between these two boundaries, and effectively you'll be connecting vectors. One vector here, the other vector here, and do a subtraction of the vector, and you get a length right here. All right, Li Xiaolong got it because he's nodding his head like this. He's smiling. Perfect. All right. So now it's a matter of locating the two values, W1, W2, on this is spiral, and then setting up two vectors, and then take and subtract the two vectors to get the length. Because the length is the intensity. The length of this is the electric field, this is the electric field, so the length is going to give you the intensity. So you understand, if you want to plot the intensity distribution, then you measure the length of this. Okay, so this is a graphic solution to Fourier diffraction. All right, so W1, W2, in fact, are normalized parameters relevant to the x, y, sometimes x, z coordinate on the screen. Okay, you just normalize it, but remember that the variable here define the two boundary of your aperture. All right, so regardless of this definition, but you knew that these two values correspond to the two boundaries of the aperture. All right, so this is how you use cone spiral. Find the vector, and then do subtraction to get the length, and this length corresponds to the intensity you'll be looking into. All right, is it okay with you? Well, number one, for Fourier diffraction, you have to evaluate this. And then this is complex number. So for whatever value integrate from 0 to something, the value is going to sit on this spiral. And then if we evaluate the aperture, the opening between two boundaries, you will be identify two vectors and take subtraction of them. And the length of the subtracted vector give you the intensity. This is the concept. All right. So we are in a position to do some real case. But before then, to be rigorous, of course, you can do some normalization. So I will let you go through this normalization by yourself. Okay. Basically, you set the normalization, you set the coefficient correctly in front of this. Okay. So that if you have a wide opening of the slit, you have a electric field, constant electric field at the observation point. This is the normalization process. So with this condition, with the condition that if you just open up this aperture, then you have a uniform intensity at the screen. So this is normalization process. Subject to this, then you put this factor in front of the electric field. Okay. In addition to this, the vector subtraction. In addition to in addition to this vector subtraction, you have this term in front of it, subject to this normalization. Right. So this is normalization process. Now let's look into one example. If I have a slit like this, so this is the right opening of the slit. Again, in the far field. In the far field, every time I'm busy with the experiment, and sometimes I don't have in the far field, this is grating. Far field diffraction is like this for grating. Okay. If we move closer, you found that it's not something like what you see in the far field. It's different now, but this has a lot of slits. And if I have just a single slit, then you saw this, right? It's a single slit diffraction. But then if we move it closer, you start to see this. You start to see this intensity distribution. It's no longer a sinc function like this. This is sinc function. But then if I move closer, hey, I found this. And we need to explain it. So this is the purpose of this discussion. So you can take it, right?
Yeah.
So this is a scenario that we want to study this because we saw something different from this when we move closer, and then just look into this spot in front of me, and then we found this, and we need to explain it. So this is the purpose. All right. So you have slit opening like this. This is bright part. The laser can go through. So forget about this RGB. Okay, so you have a slit like this, and then want to apply the theory to figure out the electric field, and then once we have the electric field, then we take the intensity of it. The intensity basically is the modulus of this C and S. How do we do this? If I want to construct the intensity, somewhere behind is the slit. So imagine that I have some slit, and then in the back I have some screen. I want to construct the intensity. All right. Let's assume that for this one, I have a slit width, a normalized slit width equal to 2, running from -1 to 1 for the W1 and W2. Okay. And then I want to figure out the intensity right at the center. So my integration for the intensity right at the center, my integration is going to be from -1 to 1. Right? I'll be calculating I'll be calculating a value from -1 to 1 to get the intensity, right at the center. Okay, -1 to 1. What is -1? Well, -1. So I need to go here. Well, this is -1.5, and -1 is right here. So I construct a vector from here to here. And +1, right here, I construct a vector from here to here, and then do subtraction of these two vectors. So this is what I'm doing right now. Identify the -1 vector, +1 vector, and then do a subtraction. The total length is this big. So the intensity right at this point is this big. It's the length of these 2 points. Okay, so I figure out the intensity at this point because I integrate the actual from -1 to 1. For -1, it's this vector. For +1, it's this vector, and they are aligned along the same opposite direction. So when you do subtraction, the total length is this big. Okay. Okay. Then it's a little bit more complicated that you want to figure out the intensity at this point. Well, the intensity at this point is running from the aperture. Well, when I say the intensity at this point, the origin of my variable moved to this location. Okay. So be careful that when in the diffraction theory, when you say that, hey, I want to know the intensity of this, then the origin for the W variable, well, you have this W variable, right, running from W1 to W2. But where is the origin? The origin of W is aligned with the location you want to see it. Okay? If you want to see the intensity at this point, then the origin of the W is moved to this point. So this is how you do the calculation. So this is the key. So once you move your origin to this point, then the left edge, of the W value has to be adjusted according to the new origin. Okay, for example, if I want to look at the intensity at -0.5 location. Okay, if I want to look at this from the center, this is 0, and this is center, and then I want to figure out the intensity 0.5 to the left of the center. Then what is the value of W1? It's -0.5. Right, if this is the center, and this is the new center, to the left of this center by 0.5. This coordinate becomes -0.5. Did you figure that? Yes, right? This is originally, if we align the origin at the center, this is -1, this is 1. Right? Now, if I move my origin to the left by 0.5, this becomes -0.5, this becomes 1.5. Can you take it? Okay. Well, one thing you want to pay attention to, the first thing you want to pay attention to is that the point you want to look at. is the new origin of the coordinate. Okay. So previously, when you want to look at this intensity, the origin of coordinate is 0 here. But then when you want to look at the intensity at this of center point, then the new origin is aligned with this purple line. All right. So this is minus 0.5 and this is 1.5. Let's look at the vector associated with minus 0.5. Minus 0.5 right here. So there's a vector coming from this to this minus 0.5 location. Okay, Yishan, can you connect a line here? You can do it, right? So this is the vector connected to this minus 0.5. And where's the vector connected to 1.5? Hey, 1.5 right here. So let's connect a line from this point to this point. So you have two vectors, one vector here, the other vector here, and you subtract these two vectors to get this purple line. So this is easy for you, right? Okay, first identify the left edge and right edge of the aperture based on the new origin. And then identify the vector, this guy and this guy. And do a subtraction, you get this line. So the length from here to here is going to be the intensity at this location. So you construct this intensity one by one, you get this kind of results. Yeah, this is a little bit tedious, but you see how people are really good when they did not have a computer. Well, same thing. Now let's open the slit a little wider from what previously is minus 1 to 1. This is now is the minus 1.5 to plus 1.5. No, 1.7 minus 1.75 to 1.75. So the width of this, normalized width of this is 3. The normalized width of this is 2. So let's just open up the slit a little bit more and see what happens. Okay. Sukai, okay. Now, previously you have small slits. Now you open it up a little bit more. And then again, you want to find the intensity at the center. Well, that's easy because if you want to figure out the intensity at the center, then you'll be rounding this W2, W1 from minus 1.75 to 1.75. And then you read the value from this to be this value. Okay. And then, for example, if you want to read the intensity aligned with this green line, this is the new origin of your coordinates. Okay, so this we want to read this intensity. This is the new origin right here. Assume that this is the from the new origin is aligned with the value 1 here. So the right boundary will be here, will be 0.75. The left boundary here is going to be minus 2.75. So to get these two vectors and subtract to get this intensity. All right. So this is how you use the cone spiral for a slit with two boundaries. Okay, again, the first thing you need to remind yourself is that wherever you want to figure out the intensity, you draw a line, define your new origin. Okay, to the left you have a boundary value. To the right, you have another boundary value. Every boundary value gives you a vector on this Coulomb spiral. And then once you figure out the two vectors and do a subtraction to get this length, that gives you the intensity of your diffraction pattern. Okay, so it's from this theory, you can explain why in the far field you have such the sinc function, but then in the near field, if you go to this point, you start to see this. Amazing. That is because we take into account the quadratic phase term in the integration. Okay. Any question about this? Well, let's go to another problem. Another classic problem. Another classic problem is that I want to figure out the diffraction. The diffraction with the edge, knife edge. So this is the sort of knife edge diffraction problem. Okay. If I have a knife edge, I might have a better luck if I just use my credit card for the experiments. Sometimes money does not work. Well, this edge is very sharp. We call this knife edge. Okay, and then I send a laser to cut this edge. This is the laser without cutting the edge does not cut the laser, and then I move it close to the edge, and then you start to see diffraction. Ooh, this is knife edge diffraction. You don't quite see structures, but if you go closer to this, you start to see some structures. You cannot find. In fact, come here. You see structures. On the right hand side, you see dark and bright oscillation of the amplitude. With this, you don't quite see much, but then here on the right hand side, you see some structures here. Okay, this is the without any diffraction. Then I start to cut it. When I start to cut it, you see that you start to have some diffraction, and then you see some dark and bright structures. A little bit not obvious, but you see some dark and bright structure. It's not a uniform split of the energy anymore. A little bit, a teeny bit. You see some oscillation with the background. A little bit oscillation with background. Because you saw beautiful sinc function diffraction already. So this is, you see the spray out of the beam, and sometimes if I go, I don't see obvious oscillation anymore. Previously, on the right hand side, I saw some oscillation. It's a constant problem. Anyway, my credit card is not enough, perhaps. But this is the we want to explain. You cannot see. You are not convinced, right?
I can't really tell. Maybe it's my eyes. Yeah.
Well, you see that there's a spray out the light a little bit, but then you see on the constant background there's a little bit variation. A little bit variation. The contrast is not good, okay, because there's a background. You see some, yeah, you do see something. You do see something in the background. It's not a constant. It's not a constant line. You see bright and dark modulation. A little bit dark and bright modulation. Yeah, you see a little bit the bright and dark modulation. It's not a constant bright line. Okay, anyway. Near field diffraction is hard to see, but you can still identify a little bit. And in fact, I'm going to show you a photo that I took a long time ago. Okay, what happened is that you see this kind of oscillation in the constant background. Because of this constant background, the contrast is not good. Okay, so but then the Fourier diffraction theory can explain this oscillation. This is quite remarkable because this cannot be explained from Fraunhofer diffraction. So we need to work with corner spiral again, and this is a little bit tedious, but you need to get used to it. Well, I just modified the handout, make it consistent with the description in your textbook. Okay, so now we define a knife edge. So this is the dark side. Okay, and you have a knife edge right here, and on the left, this is extended to infinite. This is the open aperture. So this is definition. Okay, and the upper bound of W2 or now V2 extended to infinite. So you have an upper bound integration up to infinite. And then the right edge, you have a value, W1 or V1, like here. And then up and down, you have the value between minus the infinite. So basically, there's no variation along this direction. Okay. For this, the bright side, it's all bright up and down. So you have integration for the other variable from minus infinite to infinite. It's basically just give you 1/2 in the integration. Okay. So this h is going to be the location. This h is going to be the location you will be seeing. You will be constructing this intensity. Okay, and this integration range is between this aperture. Okay, remember that the upper bound and lower bound is the boundary of the aperture. Okay, remember that, right? When we go back to this discussion, what is this? W1, W2 is the boundary of the aperture. Opening aperture, right? Shukai. Right? These two values are the boundary of the two apertures, right? Okay, keep in mind. So one boundary of the aperture is at infinite because we are looking into a knife edge. The other boundary is at infinite. So this is always infinite. This infinite gives you a value of 1/2 and 1/2 I corresponding to this point. And then we just need to identify the other boundary right here. Given different definition of the origin. Okay, when you say your origin here, you have a V1 value. When you say your origin here, you have another V1 value. Okay, at this location is your new origin. Then you need to figure out what your V1 value is. If you want to look at get the intensity here, then your origin is set to this location, then figure out your V1 value and put it into this calculation. That is the way you do the calculation. Remember this. When you want to figure out the intensity at this point, you define your origin here. And then you have V1 and V2. Now for our problem, the V2 is infinite. It's fixed already. So to some extent, it's easier than this problem. Our V2 is already fixed at the infinite. Okay? So when you want to find the intensity, this location, and so on, you define your new origin and figure out your V1. That is the key point, or that is a trick for you to do the calculation. Okay, remember this, right? When you want to figure out the intensity here, you put your origin here, and then you figure out your V1 value. When you want to figure out the intensity here, then you put your origin here, and then you have your V1 value. For V2 value, for the ninth H, the V2 value is already fixed at the infinite. Alright, so let's do the same thing. So let's do the same thing right here. Okay? If I want to figure out the intensity here, then I set my origin to this line, and then figure out my V1 value. Okay. My V1 value now starting from this is right on one boundary of the origin. So my V1 value here is equal to 0. Again, if I want to figure out the intensity, okay, if I have a great car again, okay, if I want to figure out the intensity right in line with this H, okay, so my origin is aligned with this H, but this H is also the boundary of the aperture. So my origin is set right here. So my boundary of the aperture is right here. Well, I set my origin right at the boundary of the aperture. Of course, I use V1 equal to 0 for this calculation. All right. And then the V1 equal to 0 is at this point. So these two vectors have a length. Give you a length, this length. So this length gives you the intensity right here. I label it 3. Okay. So if I want to figure out the intensity far in the shadow, remember this is dark side, far in the shadow. I want to figure out the intensity far in the shadow. Okay, move this boundary to this side. The origin is also moved to far in the shadow. What's my V1? Well, V2 is at infinite. V1 is also almost at infinite. If it is far in the shadow, so your two vectors will be very close to each other. This is almost infinite as well. If we integrate from the same point, infinite to infinite, we got nothing. All right, and that is this point. 1 far in the shadow. Because your V1, if you move your origin here, for example, you move your origin here, your origin to be here. This H is at infinite. This H is almost at infinite. Almost the same. So you're just getting a teeny length. Almost the same. This length is almost nothing. So the intensity is right here. Okay. If I want to figure out the intensity aligned at this location, well, for this case, my V1 will be a minus value because my origin is here, and this is past the infinite. This is some small negative value. some small negative value. So you just connect this to a small negative value right here. Then you do this two-vector subtraction. You get this length to go to 4. So in this region, your V1 is a negative value. In this region, your V1 is positive value. Okay, so in the end, we construct this 1, 2, 3, 4, 5. The intensity for 1 is this big. Intensity for 2 is this big. Intensity for 3 is this big. Intensity for 5, 4, 5. So you end up you construct this oscillatory curve for the knife edge diffraction. Okay. Well, you need to practice and think a little bit about this. But this page has a lot of information. Now, again, the first thing you want to tell yourself is to define the location you want to look for the intensity. And the location is your origin. And then based on the origin, you figure out the V1, V2 value. For this problem, it's particularly simple because V2 is already fixed at infinite. So you just need to figure out your V1 value. Okay. For the previous example, whenever you're looking into intensity at one location, you define your origin, and then you have to figure out your V1, V2 value based on the new origin. So this is the sort of simple two steps to construct the diffraction pattern, diffraction intensity for Fourier diffraction. Okay. Well, number one step, define your origin to be right at the location you want to see the intensity. And then based on the new origin, figure out V1, V2. Then construct the vector on this conal spiral and do a vector subtraction to take the length. Then you get the intensity. So these are the two steps you can practice and then figure out the solutions. All right. It's getting really hot, especially when I do a lot of exercise on the stage. Athens is also very, very hot during summertime. I still remember last year I was there. It was more than 40, 45 degrees Celsius.
Yeah, it's crazy.
Yeah, it's totally impossible to be outside during daytime.
Only the big.
Yeah, and in Taiwan, you also feel more comfortable to go outside in the evening when it is summer. So you see a lot of people, you see crowds on the streets in the evening in Asia. But in Athens, it's beautiful, it's really nice, but summer is very, very hot. All right. But the humidity in Athens is relatively better. All right, so this conal spiral, but then when we look into this quadratic face, in fact, we can identify some zones that could be added up to give you constructive interference. Okay, you mentioned that you have a spherical wave. You have a spherical wave right at this aperture. Okay, and the electric field at this point is given by this the integration, and then you can identify some zones that can have in phase for the constructive interference. Okay, so let's look into this phase term, and then you can define radius if this is a circular aperture. Okay. And then you can identify that, hey, within this zone, the phase change of the radiation is within 180 degrees. It's not quite changed the phase over 180 degrees yet. So more or less in this zone, the radiation coming out from this zone, you have more or less constructive interference. But then if I add this zone into the calculation, I start to have destructive interference. Once the phase changes over 180 degrees, you start to have the destructive interference. Okay, so if you could, well, the idea is that if you could block this zone, the second zone, and just do calculation for this zone and this zone with 2 pi phase change, then you can have the bright spot at a certain location. So we call this Fourier zones. So let's calculate the Fourier zones based on the phase change. Okay, so we'll pull out this phase term, and then identify that hey, there are zones you can define within which the phase within this radius on this source, the phase change is less than pi. Can you imagine that? So you have some spherical wave. Okay, you have some spherical wave. Within this zone, if you do a phase comparison between this point and this point, the radiation phase is less than pi. Within this R, you can define a zone where the phase change, the radiation phase change is less than pi, and depends on R, you can include a number of zones. So for given radius A, you can calculate the number of zones that are included in the calculation. Okay, so if I set my radius A to be this big, I will be talking about 1, 2, 3 zones. And each zone, the radiation phase within each zone, the radiation phase difference is less than pi. Okay, Suga, can you take it? It's okay, right? We're looking into, this is the radiation phase. So we're looking into the radiation phase and set this to be within a pi phase shift. And then you can deduce this R. So alternatively, if you set a radius A, then you can calculate the number of zones that is included into this A. And don't forget this R. This R is the inverse of R is given by this. And this is the distance between the field point and the origin. Rho prime is the distance between the origin and the source. This is rho prime. Okay. So if this is more or less the plane wave, almost plane wave, this means that this rho prime can be nearly infinite. So you can take this out. Okay. Well, if you have a finite radius for this wave, then this is a spherical wave, right? But if you have a source that is far away, then this would be big. So this term is going to contribute just a little to this calculation. All right. So this is the sort of Fourier zone, and then for this Fourier zone, for n equal to 1 and n equals to 3, they give you constructive interference. Okay, for adjacent zones with a phase change of 2 pi, then you have constructive interference. This will also give you constructive interference. You see the phase difference is 2 pi, 2 pi, 2 pi, the phase difference. Okay, and this phase difference is 2 pi, 2 pi, 2 pi. So if you just block this Fourier zones, then you get a bright spot from this constructive interference. Okay, but if you just include this zone and this zone, it's going to give you a dark spot. So interesting enough, think about you have a laser, and then you have an aperture here, and then you cross down this aperture as a location, put your screen, and you close down this aperture, then you start see, when you continue to close down this aperture, you see this bright and dark spot appearing on this screen. This is interesting experience. In fact, I did this experiment by myself, and then I took photo. This is not my photo, okay, but in fact I have my photo somewhere on the small Chinese textbook I wrote. Okay, you can see that you're going to walk like bright spot, dark spot, and bright spot again, bright spot, and then dark spot at the center. It's an interesting experience that if you just put a small aperture in front of your laser and then just look into your screen, you close it down. Or for this case, in fact, you just walk it along this direction. You see this bright dark spots right at the center successively. Okay. So we haven't come to this point yet, but I just want to tell you that for Fresnel zone, this is the zone where you have constructed interference together with this zone. Just skip this second zone because this is the second zone is going to have a destructive interference with the first zone. Okay, and this will allow you to construct so-called Fresnel lens. Okay, and because you sort of take out those zones, then you have the constructive interference from all the zones. Or take out those zones, and then you have constructive interference from those zones. Okay, and every zone is defined by some radius. All right. Now we haven't really changed the L yet, but in fact L is also a variable. L is the distance. L is the distance. Well, let's assume that this is almost nothing. Okay, and L is the distance from your source to your field point. So you can imagine that you can walk along this direction, and then see the zones to be increase or decrease if you walk along this direction. Okay, so now L is a variable. And what happened? Well, if L is a variable, then the number of zones will also change given the radius. So imagine that you have a laser coming out from this aperture, and then you turn it on, and then you walk along this direction. You're going to see that the number of zones, Fresnel zones, from this fixed aperture also change. When you increase L, N is reduced. Okay, so you can reduce this number one by one. Okay, you can reduce this number one by one, and then you can identify the number L one by one. All right, I'm too excited, so I overuse the time. I need to give you 10 minutes for